All right, so we're going to talk a little bit more about induction. So the very first one was sort of an introduction into the ideas of induction. What is induction? How do we prove stuff with induction? But the next thing we'll do is proofs using induction for sums and products. And I think sums and products are a very nice place to see induction proofs, because sometimes what we might do is we might conjecture a particular, let's say, closed form formula for a sum, and we can prove the correctness of that formula using induction. And so that's what we'll do today. So let's look at, well, before I do induction, this is the example, right? I want to prove, right, for, so I'll do a slightly different thing that's in the book for all n greater than 1. Okay, I'll do greater than or equal to 1, so all positive positive integers n. I could say something like sum from I equal 1 to n of I is just equal to n times n plus 1 over 2. And if you've ever taken a math class that was in, I don't know, probably pre-calculus or calculus or something, I'm sure at some point you've come across this formula. It's the sum of natural numbers. So there's a couple of ways we could actually approach this. There's a let's say a direct proof way, and I can show you a direct proof way of doing that. So maybe we'll take a slight detour, and then we'll loop back around and we'll do the induction way. There's another way to do it using what's called there's another way that we can do it. It's called, it's escaping me now. Oh, it's the well ordering principle. So maybe we can talk about that another time, but we can prove it in several ways. So here's a way. This proof is actually very similar to a proof by Leonhard Euler. And let's take a look at this one, right? So here's the non-induction way. Right. Well, this is a finite sum here, so I could just suppose that the sum, I'm going to call it S, right? S is the value of the sum. Since it's a finite sum of numbers, it should have a value. Right? And so I want to see what the the way I can figure out what this sum is equal to. Right? So this is basically what we're looking at on the left-hand side. It's the sum of all the things. And I'm saying that that sum is equal to some finite value. Well, a not uncommon way to do this is to add s to itself. So I get s plus s, right, which gives me 2s, the left-hand side. And one thing we can do is kind of think about this as 1 plus 2 plus n. And what I'm actually going to do is write a plus here. You know what? Actually, I'll do that with the plus down here. Right. I'm going to write it backwards. Since this is a finite sum, and the things I'm summing are integers or natural numbers, they have the property of commutativity, associativity, all of our favorite properties of numbers. Right? So I'm going to actually write it this way. Right, plus up to 1 or something like that, right? So in order if I were to add these together, right, I've got n plus 1, right, that's sort of if I add these. If I add these together, right, notice I've got plus n plus 1. Yeah. So I know that 2s is equal to n plus 1 plus n plus 1 plus all the way up. How many n plus 1s are there? There are n of them. So what's the value of s, right? Well, there's a 2 in front of it here. I'm going to just divide. So the sum s is equal to n times n plus 1 over 2. Right. So there was our not induction detour. Right. And let's try to see. Let's see what happens when I try to prove the correctness of this using induction. Right. Right, I could do proof. You could say the proof is by induction if I want. Right. What do I always do? When I do an induction proof, I start with what's called the basis step. In this case, this is a slightly different statement that's what's in the book, right? So what I'm going to do is I'm going to let my statement P of n be that the sum from 1 to n, right? So this is my, I'll say P of n. Right. This is that the sum n of I is n times n plus 1 over 2. Right. Now the basis, right, this is just the step I need to show that's sort of the first step, right? The very first step on our sort of ladder, our foundation that we're going to build for ourselves to build the proof up. So in this case, the smallest positive integer is 1. So I need to show that P of 1 is true. Right? How do I do that? Well, one thing to do would be to show that the left-hand side and the right-hand side are actually equal. Right? So what do I have on the left-hand side? Well, that's just the sum from I equal 1 to 1 of I, which is just 1, right? But, right, we also have the right-hand side. And what's on the right-hand side? Well, here I just put in 1 times 1 plus 1 over 2, and that gives me 2 over 2, which is just 1, right? And since the left-hand side is equal to the right-hand side, P of 1 is true. Right? So we always show the basis. Now, I kind of like to do this with the left-hand side, right-hand side stuff. The thing I'll tell you you cannot do, right? Do not, right? I will say do not. right? Do not do this. Do not say don't do this. Why? Because I don't know that this is true, right? I can't make a statement about equality, right? That's what this equal sign means. It means that these two things are equal to each other. I don't know that, right? It's not a hard thing to show, but in general, I can't make a statement of equality just at the beginning, right? That's what I want to show. I want to show that it's true. I want to show that this equality actually holds, right? So I can't say that it holds in my very first part of the steps. All right, so now we go to the inductive step. So right here, right, what do I want to do? Remember that we want to show, right, that if P of K, well, then P of K plus 1, right? So if P of K is true, I want to show that P of K plus 1 is true. Yeah. So what could I do? I could just start by supposing P of K is true, right? That is, right, the sum from I equal 1 to K of I is K times K plus 1 over 2. Right. Now this is the inductive hypothesis. Whenever you're doing induction, there's always going to be a point in the inductive step that you're going to use the inductive hypothesis, right? That's all, I guarantee that's always going to happen. There's always going to be a time when, after some manipulation of equations or doing something, right, the inductive hypothesis always shows up, right? Remember in the last one that we showed, the inductive hypothesis occurred, right? We stated that this is true at the beginning. When we used it, it was when we split things into, they include some element and they don't include some element, right? We knew something specific about the size of those groups, right? So this is going to be important, right? It's going to be important for me to know this, right? This is called my inductive hypothesis. Right. So what do I do now? Right? The next thing is I want to start at the thing something that I know, right? I want to show this. I want to start at the sum I want to start with the sum is equal, the sum of, let's say, from I to K plus 1 of I. That's kind of where I want to start. Right? So, something we might say is, right, let's see. Now, if it's been a while since you've worked with sums, or maybe you haven't done a lot of work with sums, something we can actually do, right? See, this goes all the way to k plus 1, right? But I could really think of that like this, right? If I take that k plus 1 outside, then I just add it on to the end, like so, right? Now remember, what do we know is true about this, right? By the inductive hypothesis, right? So this is where we use the inductive hypothesis. Right? Notice that I know that that this sum here is actually equal to k times k plus 1 over 2. Right? How do I know that? Well, I supposed it was true at the beginning. So it's a consequence of my supposition. Now it's just going to be a lot of algebra. So I want to combine these together. I need a common denominator. Right. So I've got k times k plus 1 plus 2 times k plus 1, right, all over 2. And I can factor this. And if you still can't see it, right, since the basis and inductive steps, true. The statement is true. Okay. So there we go. And this is one possible way we could have solved it. You can actually also start from the left-hand side, right? You can start on the left-hand side and work to the right-hand side, like what we did. You could also start from where you actually want and then get to the left-hand side, if you know what you're doing. Right? I think that's a little trickier. Or another thing you can do is actually do both of them, right? You can get the left-hand side into some form, and then you can get the right-hand side into a similar form, right? So you could you can go a couple of steps on the left-hand side, a couple of steps on the right-hand side, and if you show that both of them are equal, right, by transforming them into the same thing, then you've also shown an equality, right? But notice something you don't want to do is you don't want to start up here, right? You don't want to start here with the sum from 1 to k plus 1 of I. You don't want to just immediately say that that's equal to k plus 1 times k plus 2 over 2, right? We don't know that, right? That's actually the thing that we have to prove, right? That's what we're tasked with showing. We're tasked with showing that by supposing the hypothesis is true, can I deduce that the conclusion is true? All right.